Recording has started.
Yeah, it's fine. Let's just start talking.
Okay, so welcome back to the beginner interview workshop. Today we're going to talk about linked lists. If you check slide 2, you can have the code to the ACM portal. Remember to fill that out if you have access. So link to the slides is number 3, but you probably already have it, so that's fine. Slide number 4, we have Anna here. She wasn't here last week. This is a 4th year CS major, and she was a lead interview track last year. So today we're going to talk about Flake Lists. Does anyone know what they are? No? Okay. It's a data structure consists of nodes. And a node is basically a data structure of data and pointer. Data could be anything from, say, an integer to, say, like an array or anything else. A pointer is just a reference to the next node. It is not contiguous in memory, because whenever I create another node, the hardware decides where to store it, so it's not necessarily next to the next or previous node that I'm storing it. So usually the first node in the linked list is called the head, and the last node in the linked list will be pointing to a null value, because it's the last one. And we usually call that a tail. The link to the slides is over here. The projector is not working, so just follow along. We're currently on slide number 5. And on the right, you can see the structure of a list node in C++ syntax. That's usually how we write it. And usually we have a dummy node in front that points to the head. It is always good because then we don't have to worry about edge cases. We don't have to worry about, say, like an empty list. And if the dummy node points to itself, we know that the list is empty. So that's usually quite sweet. Okay, on slide number 6, we're going to talk about big O. A review. Last time we sort of talked about it. Does anyone remember what it is? Yeah?
The complexity for the worst case scenario. The complexity of the worst case scenario.
Correct. So we actually have 2 types of complexities. Complexity is basically how complicated your function or program is, and it's correct. It's usually the worst case scenario. And to measure it, we usually use 2 types, time and space. Time is usually the most often. We just call it big O. Well, whenever people say big O, it's usually time. And it's based on input size, which is usually n, which is called O of n, or like O of n squared, meaning that the size would be n squared for like in terms of time. So then based on input size, say if my input size is n, and my big O is n squared, meaning that it will double every time I run my program, right? And for space, it's basically how much information I'm storing when I'm running this function or program. Okay, so given that information, can anyone guess the big O of arrays? For accessing? No? Yeah?
Is it just O of 1?
Correct. It's O of 1 because you can basically access it through the random access, the brackety things, right? You can do, don't recall. Like for arrays, you can do like bracket 0, and that's like the first element, right? So that arrays give you random access. It has big O of 1. For insertion, arrays traverse through everything and add it to the very back. It has a oh my god. Okay, I cannot speak today. It's okay. Arrays insertion is of n because it usually adds to the last element. And then for deletion, it's also of n because when you delete whatever element, you gotta shift the whole array, right? So say if the array is in the middle, I want to delete the middle element. I need to go to the middle element, delete it, and then move everything behind it back, right? So that would be all of it. For searching, same, because I don't know which element is stored where, so I need to go through the whole thing. So that'll be all of it. Okay, give it.
Okay. Let me explain why insertion for array is going to be O of n instead of if we it would be O of 1 as in for linked lists, right? So when we have this array and it's contiguous in memory, we want to make sure that wherever we insert, we think of the worst case scenario. That's exactly what time complexity is, right? So if I wanted to insert this at the end, that's fine. In C++, it's nice if you just insert right at the end. It will just move, it will give you an extra block, and it'll just be like, here you go. But worst case scenario, we're actually going to insert right at n-1 of the entire array. In this case, C++ is like, okay, well, we need to copy this entire structure first, and that takes O of n, right? Because we gotta copy element by element, and then we insert within here. I'll put a 6 here. But within linked lists, you have to realize that when we insert, we can just set the next pointer so from next, it's actually going to be, maybe this is 4, so next is 4. When we want to insert within a linked list, then we can just make a new node, and then we say, okay, call next, that it will now point to here. When we insert that, then we can make sure that the new node, let's just call this 6 again. We make sure that 6 next is now going to be pointing to 5. Oh, sorry, this is 4. Okay, never mind. So 6 is now next is going to be pointing to 4, and then in this case, inserting is still O of 1 because it's going to be like whatever we want. But remember, if we want to see like, okay, we want to insert like a 6 right before 4, we still have to traverse through whatever number of elements beforehand. And that in that case, search is always going to be O of n, worst case scenario as well.
Good.
Any questions on why the big O is what it has on the table right now? Okay.
So I guess we're on slide 10 then. Okay, the property of linked lists. They're good because they're dynamic data structures, meaning that we can change its size whenever during runtime. So then say like my program is running and I want to delete something or like add more things to it, I can always do that. Unlike arrays in C++, which we have to define the size first and we can change it after that. It is also easy to implement and for other data structures. So we can use linked lists to implement stacks and queues. If you guys don't know what they are, it's okay. It's another data structure that you will probably learn in CS32 or later workshops. And as we said, it's easy for insertions and deletions because it's a constant. It's not good because it's sequential, meaning that to access or find, we have to use our big O is O of n. So if you still don't get it, just think about like alphabets, right? Like if like I ask you like, oh, what is like Q in the alphabet? You usually sing the song, right? Yeah, like that. So there are also more types of linked lists. The one that we just talked about is a singular one. So we can also have a singularly circular one, which basically has to tell the last node pointing to the first node, the head node. We can also have a doubly linked list, which just has 2 pointers instead of 1. So usually we just have 1 pointer that points to the next, right? For doubly, it has next and previous, so you can go back. For a circular doubly, you can basically, well, it's doubly plus circular, so it's pretty intuitive. You have 2 pointers, points to next and previous, and the last node's next one is the head, and the head's previous one is the tail. So on slide 12, there's a little check your understanding problem. Can anyone tell me which one is the circular singly linked list? Anyone? Yeah?
The first one?
Can you indicate sort of where on the slide, like top left, top right, or at the bottom?
Oh, top left.
And what's your reasoning?
Because it like the last element, or I'm not sure I'm using the right word, but the last element, like, its next value is the first element.
Yeah, thank you. That is very, very correct. How about a circular doubly linked list? Yeah?
The one right next to it, onto the right.
Mm-hmm. Do you want to explain it?
If we look at, there's arrows pointing to what is basically the previous node. So if you follow the head, see it goes all the way to the end or the tail.
Right.
And the tail has a pointer that goes all the way back to the head.
Right.
There's this back and forth operation of nodes.
Right, that is true. And a doubly linked list. Should be a free point. Yeah?
It's the one we didn't talk about yet.
Correct. Very smart, very smart. Okay. Okay, any questions so far at this point? No questions, good. So right now, we're gonna go through to make sure that you understand the concept and also the syntax a little bit. We're gonna walk you through a problem. So on slide 13, you'll see a little problem that's like sort of easy. So they want you to write a function to delete a node in a cyclically linked list, but instead of giving you the head, they'll give you the link to the node that they want you to delete directly. So also it's guaranteed that it's not the tail. So you just delete like somewhere in the middle or the head. Anyone have any idea about how to approach this? Give you a couple of minutes. Yes?
It's interesting because we're not starting at the head.
Right.
So
So what can you do with it? Think about the properties of a linked list.
I guess because we're only looking ahead, we can try to just look ahead. And we can't look back, so there's only one choice, which is forward in the list. And try not to delete the thing, but actually just like make it all of the successors. And delete the successor instead.
Delete its successor instead.
This is really loud, sorry.
Can you slow down about
So my guess basically is to try to copy the successor and then just remove the successor out of the list instead.
That is a very interesting idea.
Then
What is she doing?
And are you writing on the problem?
Oh, I could, but I was writing down the properties of the.
Oh, okay, so what's your name?
Daniel.
Daniel's idea is completely, well, very correct. So what we have in mind for this question is that we have a target node, as you can see from slide 14 and 15. What we can do is we look at the node right after that. So it's next node, which you can see on slide 16, the green one, or like turquoise. And what you can do is you can copy the values over, right? So as you can see from slide 17. And then the next thing that you can do is you can remove the reference, or like change its reference from, because you were pointing at the directly next one, right? So what you can do is you can point to the next one's next one, so to after that one instead. And then so what happens is that right now you basically have, well, on slide 16 you 17 you basically have duplicates, right? So you sort of remove your the note that you need to remove because the value is gone. But you have a duplicate, so on 18th you change your pointer to the next one's next one, meaning that the next one is gone basically. It's not in the linked list anymore. So then the list would be, if you go through the list, which is like from 19 to like 25, when you use the head node to traverse through the whole thing, you will not traverse through the original green node. So you basically sort of deleted the node. And if you look at slide 26, you can see the syntax for that solution, which is basically 2 lines. But this is a good question because you can also talk to your interviewer about like how to approach the problem, because can anyone tell me why this is not a good practice necessarily? Go ahead.
There's no way to access the node you kind of just deleted.
Right.
You didn't actually delete it, you just removed all reference to it.
So for this question, to delete it faster, we didn't actually delete it. We copied the value and then we removed the reference. But then that one's sort of just like dangling over there. We have no way to access it or delete it, but it's faster, but it's not good practice in real life. So when you talk to your interviewer, you can ask them whether or not it's okay to have like some sort of memory leak, or like if you want like speed over like space, blah blah, like things you can talk about. These are all like things you can talk to your interviewer about when you're solving the problem. That's like a good thinking process.
I just wanted to, let's brainstorm. Like, since Katie's question initially gave us like a compromise of saying, okay, we're never going to delete from the tail or the head. So let's think about what would happen if you were to delete the head or the tail. Does anybody have some suggestions on what would we do differently? Or I guess what conditions must we have before doing that? Because we're given a property of, so we're giving one node, right? And then we have the properties. It's usually just we have the class method of it would be a next, and you go to the next node, as well as the value of the node that is right now that we have. So what would be different if we were to delete the head node? So what conditions would we have to have in order to do that? Any, okay?
You would have to have a node like after the head. If the head was the same as the tail, then it would make it messed up.
Right, so first I would check, if there's only one node, so if there is no next, let's just pretend like this was a null. If we were to delete it, we would have an empty, or just an empty linked list, right? So we have to take into consideration of that. But let's just say that there is a node. So what would be some of the things that we have to keep in mind? Okay, well, let's see. Let's erase this. So we were given the head, right? But under the condition that we know it's the head, what do we do? Okay. Under the condition that we know that's the head, we can immediately just say, okay, we can make sure that we traverse first to the next one, right? Well, we keep a dummy node. And in this case, it's not really dummy. It's just we want the reference so that when we delete it, there's no memory leak when we exit the program. So you just call this head. And then we want to immediately traverse to the head.next. So you just like do, next pointer, like head pointer. Actually, you can not call this head, but head equals head.next. So now we just lose that reference, right? If we didn't have dummy equals head. Because this is a singly linked list, that means that we can never come back after we just traverse through head equals head.next. After that, we can delete dummy, because we still have that reference. It's just like we can never access it again. Doing that will make sure that we will not have a memory leak. That's specifically for the head pointer. Does anybody have any ideas for the tail pointer itself? If we knew it was a tail pointer, what would we do differently?
Can we just set the value to null?
Yeah, we could just set the value to null as well. I feel like that could be a little hesitant. You would probably want to delete it first because memory leak, and then you can just set the value to a null pointer. That would to the net. But since technically we don't have access to the previous node, so the previous node would point to null. So that's good. After that, okay. Some good brainstorming to think about, just how you would approach the question if it were worded differently. Okay.
Okay, so is everyone clear about deleting a node in a linked list, given the address of it? Okay, so before we move on, we have a choice right now. The projector here is broken, but we've set up the projector in 4760, which is exactly 2 floors above us. So if you want to move up 2 floors, we have a working projector, or you can just look at the slides on your computer and we can stay here. So it's up to you guys, whatever you want to do.
Do you like it that we whiteboard out in front? Because we would do it regardless, but it's just like, I write really loud, so I'm really sorry.
Let's see like a raise of hands on who wants to stay here.
Okay, that's quite a bit. And then otherwise? Okay, unfortunately for the people who chose to go upstairs, I think we're going to just stay here then. Which is completely fine.
Okay, if you check slide 28, we have a warm-up prepared for you guys. Hopefully you guys have enough knowledge to solve it easily. You can find a pair like last time and work through it like interviewee, interviewer style. We'll give you guys 10 minutes, 5 minutes to solve it.
Okay, and if you don't have a partner, just raise your hand and we'll try to.
And then if you want to talk to me, I'm completely fine. I can be your interviewer, you know, just like talk to me.
Yeah.
And every other person that's standing up here will be more than willing to talk to you for anything.
We're also gonna do this interviewer style, but instead it's ICPC officers, so you guys can see how you should approach it in real life. So for this question, we have Anna here as the interviewer and me as the interviewee. So she is the interviewee and I am the interviewer.
Oh, so
Sorry.
do whiteboard? Okay.
Yeah. So she is gonna approach the same problem, and you guys can see her how to solve it.
I'm not tall enough.
Here's fine. Oh, okay.
So I did talk with some of you guys, I guess 2 groups, and then we came to pretty similar conclusions on how we would approach this question at first, right? So does anyone want to give me a pointer? I mean, I know this already, but what was your initial idea when you saw this question?
Just traverse through the linked list and find the link first.
Sorry, the door closed on you.
First like traverse through the linked list and like find the link definitely.
Yeah, exactly. So when I see this question first, I see, okay, we're given a head and we want the middle node. So when I think of that, I know that a linked list, we're not given a size. So we're gonna have to traverse it regardless in order to get the total size. And then its second comment says, if there are 2 middle nodes, return the second middle node. Then I have to care about if it's an odd or even number of linked list nodes, right? So we want to check if the total size is going to be even or odd. So let's code that out. So just call this whatever you're returning a node. So it's a node star. And then I just call this solution. Okay. So edge case wise, I can first be like, okay, what if the head pointer that they give us, you know, it's null? So that could be something that we check first. We can just say if. Oh wait, actually it was given. And then I'm just going to assume that the node struct or class, depending on what we're doing, is going to only have a next method as well as a current value method. Doesn't really matter in this case, but that's what I'm going to be assuming. So if head equals null, there's no list. So in that case, let's immediately return. We're just gonna, what you can ask your interviewer, be like, what happens when you have an empty list? And they'll be like, okay, well, good for you thinking about that. You can just return null. In my case, I feel like I'm gonna run out of room. Okay, so what's my next condition? Okay, so first I want to traverse the entire linked list to get the size, right? So let's do a while loop. So while head doesn't equal to null. And then I'm thinking about this, I'm like, oh wait, I kind of want to make sure that I still have the reference to the head pointer when I traverse it. Because remember what I was just saying right there, if you traverse it, you're actually never going to get it back because it's a singular linked list, and then once you traverse it, it's gone. So let's put one thing here, which call this OG head or something, node. Okay, so we're going to first traverse the entire thing and make sure you don't write your code as big as I do. So we're also going to have a counter, right? So int counter equals to 1. Why can we set it to 1 and not 0? Yeah, so we check at the beginning if it's null. If it's null, we return immediately, and otherwise we can just iterate the counter. Sounds good? Okay, so next we're going to do head equals head.next. And remember, we can do this because we're assuming that there is a struct and there's a next field. Sounds good? And then we do counter plus equals 1. Okay, so after we count everything, let's just say we have this list right here. That couldn't give us 5, right? So what do we do after? I regret using this board. Okay. And so after that, we see that this is technically 5 elements. So you guys know what happens when you divide an odd number by 2, right? What happens in C++? If I did int total size equals counter divided by 2. What happens there?
It'll round down.
Exactly, it'll truncate it actually. So in this case, what is the difference between having divide by 2 and then for odd and even, right? Because for an even, let's say we had 1 through 6, we'll actually get 3. But in this case, since we want the second middle node, we're actually going to do 3 plus 1. Let's see for the odd case. So for odd, it would be 5 divided by 2, right? This in C++ will truncate to 2, but then we want the third element anyway. So when we do plus 1, it actually doesn't make a difference for odd and even. Make sense? Okay, so let's do that. Count divided by 2, and then we're going to plus 1. And then obviously if you do int, it'll cast it to an int. Very nice. So next up, does this make sense? I'll erase it in order to, oh, question?
I'm pretty sure it's supposed to be head, like arrow next instead of head dot next.
Oh yes, sorry. Thank you. Okay, this makes sense? We're gonna move on to the next part. Oh, this is not turnable?
It is.
Oh.
Maybe
Very like chemistry. Okay. So as Katie is so generously erasing the board for me, what is the next step that I would do? Quite anybody? Yes.
Just iterate as many times as possible.
Exactly. So let's do that. And so we had total size up here, so let's just like remind ourselves we got total size. And then we also had OG head, right? So we kept track of that. If we didn't keep track of that, it was kind of sad because then we can't actually get it back. So what we're gonna do, so we're gonna have another counter. Let's just do counter equal to 1 OG head because we're already at 1. Let's do while. I think it'd be counter less than total size. Wait, total. Wait, what did I count? What did I call it? Did I call it middle? Oh, I didn't actually call it correctly. Okay, so I did total size up there. Oh, this is not that big. It's actually not total size. It's like middle. Sorry for the miss. I can't believe I called counter twice. Ugh. Let's just call this traverse, because I'm not very good with my naming variables apparently. Also, always try to rename your variables during the interview with something descriptive. Don't do I or J unless you're within a for loop because it's non-descriptive and then sometimes the interviewer could get confused. That's something I learned. So while traverse is less than middle, we're just going to iterate the OG pointer. After that, let's just return OG head. Sorry for calling it OG head, it's kind of confusing. Ow. So let's walk this through. So always try to test out your test case, and I feel like I did something wrong here because it's like less, but I'm not sure if it should be less or less than or equal to. So let's do 1, 2, 3, 4, 5. So we have total size equals to 5, right? And then 5 divided 2 plus 1, so it equals to 3. Let's try. So traverse is 1, so 1 is less than 3. OG head, we're currently pointing at 1, so we're going to go to the next pointer, it's at 2. And then we come back, and oh, we didn't traverse plus equal to 1. Right? And then after we're going to go to, that's equal to 2 now. Is 2 less than 3? Yes, it is. OG head equals OG head dot next. So now we're at, we're going to 3. The traverse is still at 2. And wait, hold on. What did I just do? 1, all traverse, 2, goes to 2, and it goes to 2. And then we're going to go to 3. Okay, yeah, this goes to 3. And then traverse equals to 3. 3 is not less than 3, therefore we exit out this while loop, return OG head. Make sense? Does anybody tell me what the time complexity is? Or I guess I should tell you, since I'm the interviewee.
Yeah.
You didn't really.
Complexity?
Okay, so if we go back here. What's the worst case scenario? If I guess it would be O of n divided by 2, right? Well, actually for here, we're actually going to traverse the entire thing, so this would be O of n. Since it's not a nested loop, we're actually going to, nested loop is when we're actually going to have O of n squared and beyond with the exponents. Since this is not, it's going to be O of n plus O of n divided by 2. And that, in the worst case, we would just, if we take the, I guess like, if we take the limit.
We only take the biggest
Yeah.
of everything. So then we take the biggest term without constants. So that'd be O of n.
This will round down to O of n. Approximately O of n when you get to a really big input size. Okay, so this is the, what's it called? The brute force method in my opinion. But when you guys are like listening to me talking, did you find a better method of possibly doing this in one pass instead?
Go ahead.
I guess you could store initially 2 pointers to the head, and one of the pointers you like increment it twice, or the other one you increment it once. You just keep doing that until the faster pointer hits the end, and then the slower pointer is just your answer.
Right. Great idea.
That's
So what's
amazing.
something you have to be aware of for it traversing twice as fast, right? What would happen when you hit an odd pointer, and what are the conditions, I guess, like when you think of that? Odd and even, like depending on that.
I guess for the fast one, you just have to check after its first increment that it's not null, I guess.
Mm-hmm.
But I think the answer is the same with even if it hits null like 1 step early.
Okay. So, okay, do you want to move on to this?
Yeah,
Like,
someone has a question?
However, we check for the pointer, this one will be on, the first one will be on, and the next one to it.
sorry, what did you say?
Okay, so, because there are 2 cases, there's odd and
Right.
even, right?
Right.
So let's say, if you have something like 5, there's a 5 elements, so we'll go from 1, 3, and then 5, and that's sorted. If you have 6, we have to go 1, 3, and 5. So what if you check if the next element is the 5 or the empty one or not?
Yeah, so we have to check both that the next pointer is not going to be null as well as the
The
pointer.
final point is not.
Exactly.
Yeah.
Yes.
So you're saying the fastest way to this whole problem is still gonna be O of n?
It's still going to be O of n, but instead of doing it where we find the size initially, so that's O of n, but then we traverse it again, so actually it's O of n plus n divided by 2.
Yeah.
It would just be O of n without this.
But it's still O of n.
Still O of n. But, you know, your interview could be mean and be like, hey, do you have a faster method?
Yeah.
So,
If you know a faster method, you always do it. You know?
Okay.
Yeah.
but yes,
'Cause,
it's
like,
still O of n.
If the big O is the same but slightly better, like more optimal in some way, you always gotta do it.
Okay. What just happened?
Okay, so what's your name? Ethan had a really good idea. So this is what we're gonna talk about. Some people call this Floyd's method. Some people call this fast and slow pointers. Some people call this hairs and the tortoise. So basically, the idea is to have 2 pointers that pace differently. This method is good for cycle detections. So the thing that finding the middle node, which is the thing that we just talked about, or cycle detections, which is another problem that we will be doing later. And these, the fast and slow pointers usually is incrementing by 1. The slow one is usually incrementing by 1 every time. That's slow because it goes through every element. Whereas the fast pointer usually increments by 2 every time. So it's like every other node. So the idea is that if we look at the linked list, the idea is that we have 2 pointers, right? Fast and slow, blue and red. And then if our fast pointer moves first, it increments by 2, right? So it jumps from node 1 to node 3. Yeah? And then our slow pointer moves in the same iteration. Our slow pointer moves to node 2 because it incremented by 1. Yes? And then on the next iteration, the fast pointer traverses by 2, right? So it goes through 3 and then 4. 2 steps, right? But it's a cycle, so it went back to 3. And then on the same iteration, the slow pointer reaches 3. And they match, so we know that there's a cycle. That's the idea behind fast and slow for cycle detection. So this is the warm-up exercise that we talked about. Supposedly, this is, we want you to use the cycle detection / fast little pointer method to solve this question. I guess you guys can do it when you in your free time, just to like code the concept up instead of, because like knowing the concept is usually different from like actually coding it. So you still gotta practice it. But right now we're gonna do another problem, and using the same technical interview techniques that we talked about in the first workshop to solve this another linked list problem. So I believe this question is is it Justin? Bill? Someone's question? So we again are doing this interviewee stuff.
I can do this one.
And these are these are the technical interview approach that you should be following.
All right, so let me follow.
Are you ready?
Thank you. All right, cool. So can all you guys see this, or if you can't, I guess pull it up on the slides. Okay, so hopefully all you guys have it up by now. I'm gonna try to follow the steps and pretend I'm an interviewee, and Katie's my interviewer. And so the first thing I would do, the first thing on the steps is to kind of try to repeat the question in your own words. Of course, that means reading the question first. So let's get this problem together. Given head, the head of a linked list, determine if the linked list has a cycle in it. And so basically what a cycle is in a linked list is that if you can follow a path infinitely in a linked list. And so one node will eventually point to a node that you previously visited, which means that if you try to traverse that linked list normally, your program might not halt, right? And it might go on forever. And so basically the way that you can find out, I think this problem even pointed out, the way you can find out if there is a cycle in the linked list or not is by realizing that you visited a node that you've previously visited. And so I think we agreed that we want to read the question in our own words. So I think that's something that we've done. And so the next thing that we're going to do is to check any assumptions and ask any clarifying questions. So for this, for example, all right, Katie, so what should the return output be? What data type is it? Is it a Boolean or is it an integer? What represents whether or not there's a cycle?
You should just tell me whether or not we have a cycled linked list.
Okay,
So
a Boolean, awesome, great. Is it possible for us to be given a null pointer, so no linked list at all, and does that count as having a cycle or having no cycle?
For this question, you will not consider that case.
Okay.
So it's fine.
Great, sounds good. And is there, let's see. Okay, I think that's actually all the questions I had.
Alright.
But again, you can feel free to ask other questions if you are unsure about the parameters of the question. And so let's open it up to see who else has any questions for Katie, the interviewer.
No question? Alright.
Okay, great. If no one else has any questions, let's head on to the next step. Run through a real example, right? So remember what this means. This means thinking of a unique example. If you're whiteboarding, for example, it might be useful to draw your example on the whiteboard. And so let's say, we have a linked list 1, 2, 3, 4. And this is how the linked list looks. And we're given the linked list starting at 1, right? And so, according to this problem, does this linked list have a cycle or not? I know it's kind of trivial, but yes? Yes, it does. Okay, great. And let's say you get another linked list that is just 1. Does this have a cycle or not? Does the second linked list have a cycle or not? No, right. Awesome. And so the examples for this question are a bit easier to determine by just like human intuition, whether or not the result should be true or false. But this can be super useful in problems where it's not immediately obvious to the human eye whether or not you know a linked list has a cycle or not. But like obviously we can see the cycles pretty easily. All right, great. So let's move on to our next step, which is brainstorm solutions and their time and space complexity. So we're going to give you guys 2 to 3 minutes to do this while I also brainstorm, and then we can kind of go around as officers and we'll like take people's ideas and we'll see what you guys come up with. So yeah, take 2 minutes and then we're going to continue the rest of our steps. So pretend you're thinking like you're in an interview right now. Yeah.
The last one is going to be no, right? So then if they add a then so if the fast part is supposed to or ever
Okay,
then
so
how does that thing
this is something you might want to ask your interviewer,
so
like,
then
you
the
modify
fast part
the
is cycles around
and
it.
as your interviewer,
You can do it in a minute.
Yeah, so that means that there's a cycle.
Which is the worst case scenario.
how about do this complete in place? Just like do not create a new document.
You guys have any ideas?
Yeah, so board out next will be no.
You know why that works.
That is the question.
Okay, so I think a good idea to start with is how fast the cycle pointer that we
Is that faster than the cycle or is it faster than the
why
longer?
don't you elaborate on
Just
that?
keep moving until the second.
Okay, we'll look at this. So let's step by step. Let's start both sides. Once you agree,
Another reason why
so then the next one.
you know what your more specific
So yes, so that's.
yeah, that's fine.
So my understanding from the question, I didn't
Usually can just go over, but I think saying old and plus modifier is do and saying well, that will, that will event, that makes you shows that you guys know what the score is doing, because you know that it's something.
Oh, this is my bar phone. You guys are. They already got it.
They
What they changed is.
Yeah, but like when you start walking more, it's
Exactly that. I guess like you
Yeah, I think they had email and then they give you a model balance because some of them come until a few days. I don't know about that. It was like something like we wanted to know. There's I think we okay, good stuff. So I think we've had enough time to think about it. And so I'm gonna try and explain what I heard from you guys.
All right, Bill is gonna start talking now.
All right, cool. So we went around, and it looks like everyone has come to the kind of same idea of using what we had previously learned in our last question, the concept of having a fast and slow pointer, right? And so the whole idea is that if we have a cycle, right, in any linked list, so let's say this one, and we know the cycle length, so this is a cycle length 1, 2, 3, 4, 5, 6. Then if we have a fast pointer that, let's say, travels at twice the speed of the slow pointer, so the fast pointer will travel at twice the speed, so once the fast pointer will immediately go to this node, and the slow pointer will go to this node. We know that if there is a cycle anywhere, that means that the distance between the slow pointer and the fast pointer from the other side is always going to be decreasing, right? And so if the cycle length is 6, we'll have like the outer distance starting from here is 6, and then it becomes 5 because the fast pointer moves faster, and then it becomes 6, it becomes 5, 4, 3, 2, and then 1, and then eventually they'll meet, right? Because that distance, when it reaches 0, it means they've met back again. And you know that this works because if there is no cycle, it means that you can continuously run this program until the fast pointer reaches a null pointer, right? And so in the end, you really only have 2 conditions you need to worry about. 1, if the fast pointer reaches a null pointer, and 2, if the fast and slow pointer meet again, right? And so now that we have our brainstorm solution, let's think of the time and space complexity. So obviously, because we're only using pointers, what is the space complexity? Anyone have any ideas? Right, it'd be a constant space complexity because we obviously are only using pointers of constant size and we're only using 2 of them. And what is the time complexity? Yeah. That's right, O of n. And why is it O of n?
Because you don't like, you just do one thing for each node, kind of.
Right, so the idea is that if there is a cycle, it's going to take you at least traversing the entire cycle, right, to find where the cycle is. And if there's no cycle, it's going to take you at least traversing the entire linked list. And so in the case of if there's a cycle, in the worst case, the entire linked list is a cycle, it's a giant loop. And so if there's n elements in the linked list, there's going to be O of n traversals. And then in the case of no cycle, you're going to go through the whole thing anyway, so that's O of n in the worst case. Awesome. So now that we're done step 4, we can finally go to step 5, write working code. Awesome. That's going to be very fun. All right. So quickly, this shouldn't be too difficult. Let's say on a bool. Has cycle. We can take a node. And so before, Katie mentioned that when we ask clarifying questions, that there cannot be, we cannot be given just a null pointer, right? And so we can ignore that case, but there are also like 2 kind of like easy edge cases that we can just take care of right away. So we know that if head, since we're not given a null pointer as the head, we can successfully dereference the head without worrying. And so we know that if head next is null pointer, then we know there's for sure no cycles, because it just means you have a head node and you just have one node, like the example I showed before. And so we can return false. All right, and there's another easy test case. If the head points to itself, we also know that's like the simplest cycle we can have. Awesome. So we've got these like really easy cases out of the way. We can start implementing an algorithm. So we need a fast and slow pointer, right? So we can set slow to head. Can everyone see my handwriting? I know it's a bit small. We're good? Awesome, thank you. And because now we've cleared kind of in our first 2 cases all the possible test cases for if there's only one node, and of course Katie mentioned that there is no case when there's 0 nodes, then we can immediately set fast to, actually, this doesn't matter, we can just still set it to head. Okay. All right, so we can set fast and slow to starting at the very start, and now we can write our while loop, right? And so we know that our stopping condition here is going to be if we reach the end of the linked list without having found a cycle. And so we want to check if the fast pointer is null pointer. Right? And so here, what we want to do is now we want to start traversing the linked list. And so we can set slow. Right? And then we have to pay attention here because we've only checked here that if fast itself is null pointer and not that what fast points to is null pointer yet, right? And so we can't fall into the trap of trying to dereference what fast points to if what fast points to is null, right? Because we're jumping to a head. And so that's something that we need to check to make sure that we don't like do a site fault or anything bad happens. So we know that if what fast points to is null pointer, then we can directly return false, right? Because that means that the fast pointer can't actually go on and we've reached the end of the linked list. Next, we can iterate the fast pointer. So we want to do this twice. And finally, we can check if the fast pointer equals the slow pointer, then we can return true. And here, keep in mind we're comparing the pointers themselves, and so it doesn't matter if they have the same value. If they point to the same object, then it'll work, right? Okay. And obviously now, if we've traversed the entire linked list, we know that this condition has been met. So like fast is now null pointer, and so we can return false at the very end. Awesome. So that, I think, is the solution to the problem. Of course, there's also step 6, which is to test your code, but I will leave that up to you guys, and we can move on to the next question.
Alright, so for the next question, we are trying to, actually I will have Lenny do that. So we also see technical interview stuff.
I can erase it and then we talk about it. Okay. So basically for this question, you're given, I think, the head of a linked list. And
I don't think they see that question.
oh. Yeah. So you're given the head of a singly linked list, and the goal of the problem is to reverse the list and then return the reverse list. So I guess I'll wait for Katie to finish erasing. Yeah, so like I have a question, which is when it says return the reverse list, does it mean like we're returning the head of the result?
Yeah, so the head that you need to return would be the new one, right? So then supposedly the tail would be the head. You return that one.
And then I see that the number of nodes in the list is in the range 0 to 5,000. So does this mean that there can be like an empty list?
There could be an empty list. That would be a possibility.
Okay, that sounds good. So, okay, I guess everyone here, we'll give you guys a couple minutes to think about an approach to this problem, and then I will be the interviewee and solve the problem on the board.
Do you guys want to talk about the problem? Think about it. I'll give you guys 2 minutes. Alright, starting now.
I think for this problem, you're not allowed to create new nodes. I don't know if this is an existing list.
I'm just thinking. I got a ton on it. Jacob Day is coming. And yeah, so I'll get that. So like $6. What do you set up?
I think the first step of this conversion I want your
Okay, no. Okay, I guess you can just sit. Maybe Aaron. But like all the way through these is out. It's so easy for me.
It is.
So I don't know what
Yeah.
happens.
Does that mean that?
I don't think so. I think that was definitely the slowest one.
Yeah, your performance were big.
Alright, time's up. We will have plenty of questions.
Okay, so for this question, let's just first draw out like an example of a list that we want to reverse. So I'll just make like a shorter one than what's on the problem. So I'll just do like 1, 3, 5. And then what we want to do is, so basically for this question, I believe that we can't create new nodes, right? We have to work with the existing list.
That is a good question. Can you think of something that's better? Like, can you optimize the space complexity? You
Yeah.
can, but maybe there's a better way.
Yeah, so we're not, basically we want to use like the nodes that are already existing and then,
That would be best, yes.
yeah. So what we want to do is, you know, like these arrows, they're currently pointing like in this direction. And then what we want to do is like, just flip the arrows somehow so that the nodes, they stay in the same place. Like we're not making new nodes, but we change where their pointers go. So for this, oh. So for this, basically our goal is just to work with the pointers that are in the current list that we're given. So let me start writing the solution. Node reverse list. And then we're given the head. So okay, so first I think we should check for like the edge case, and in this case it's gonna be an empty list because an empty list, it doesn't have any like nodes or pointers or arrows to begin with. So if head is null, then we don't need to do any reversing, so we just return head. Otherwise, what we want to do is traverse the list and then flip the arrows as we go along the way. So to visualize this, we can have, well, first, yeah, so we're gonna have definitely like a pointer that starts here, is like head. And then the idea is to have like a pointer, let's call it like P1 to the current node. And then we're gonna move P1 along the list. So next P1 is gonna come here. And then now we want to, what we want to do, like currently 1 is pointing towards 3, right? So we want to like, and 3 is pointing to 5. So what we want to do is put this arrow to here, like, so that 3 is now pointing to 1. And similarly, we want this arrow to just point like towards null. So if we want to do this, if we move like 1 pointer along here, we cannot go back to the previous one. So what we want to do is have another pointer to keep track of the previous node that we came from. So let's just call this like P2. And as P1 moves along, we know what the previous node is. So we can just set like this pointer to the previous node. So basically we need to have like at least 2 pointers traversing along the list, one keeping track of the previous node and one keeping track of the current one, and then set the current one's pointer to the previous one. And in addition to that, once we flip this arrow over, so once we like have 3 pointing to 1, for example, then we kind of also lose track of 5. So before we change the arrow, we also want to keep track of the next one. Let's just call this next, so that we can continue moving P1 along like the original list. So does that make sense to everybody? Yes? Okay. So I will. Okay. Whoop. Okay, so in this case, at the end, we will return the head of the reverse list. And so we can just keep the head pointer, and that's going to be P1 in like the diagram that I drew previously, because it's going to traverse the list and go to the very end. And then, so this is going to be a while loop. So we know that we've hit the end of the list when head becomes null. So we're going to do while head is not null. And then so first we need to keep track of the previous one as well as the next node in the list. So we're going to make a new node called next. Which is heads next. Or I think we can just put as head. And then I think I should probably create like another node here. So let's, okay. And then here I'll put another node. Let's call this prep. And prep is just like the previous node in the list. And when we begin, it's null because the previous one before head is nothing. Let's call it null. So now we have one that's pointing at the current node, one that's pointing at, sorry. So I think next should be heads next. One that's pointing at the next node and one that's pointing at the previous node. So now we're going to start moving the pointers along, and then as we go along, we're going to flip the pointers on each node. So first we want to set heads previous. Yeah. Oh, sorry. My bad. Heads next. Yeah, heads next is previous. My bad. And then now, so what we have is like null. So what we've done is originally we have like, so this is head, this is prep, and this is next. And so now what we've done, heads next is now pointing to previous, which is null. So now we flip this arrow. And then in order to go to the next node in the list, we have to set head equal to next. So, or sorry, before that, we actually should set prep to head, because otherwise we lose track of head. So what we're gonna do next is prev equals head. So now prev is here. And then now we can move head along. So head is equal to next. So now head is gonna point here. And then we're going to, so this is like pointing something somewhere else. And then I think this is done. So now in the next iteration, head is still not null. Let's suppose there's another one here. And we put a new next here. So next is gonna be heads next. And then heads next. So we're changing the pointer now to prev. So this pointer is gonna point at the previous node again. And then we set prev as head again. And then head becomes next. So we just keep doing this until we reach the end of the list, which means that head is null. So let's say there are no more nodes left in the linked list. And at this point, next is gonna be heads next, which is like null. So next is gonna point at null. And then heads next, it's gonna be prev. So we did that already, and prev is gonna be head. So we're gonna put it here, and then head is gonna be next. So head now also points to null. And now at the end of this iteration, we realize that head is null, so we're gonna break out of the while loop. And notice that prev is now pointing at like the beginning of the reverse linked list. So at the end, we're just going to return prev. And then we are done. So for this problem, you'll need to keep track, or you'll need 3 pointers to keep track of like the current node, the previous node, and the next node until we hit the end. Yeah.
Questions? Questions? No? All good? All good? Yes? Yeah? Okay. Okay, so since you guys are all really smart, we're just gonna do a harder challenge question. Since it's a little bit harder, I'll give you guys 6 minutes to talk about it, and then we'll have one of our officers do it. Interviewee style.
Such that complexity is only a
function of like this, the time, the number of nodes to complete into the join point rather than the whole run. Because they assume like maybe the merge point is like 10 million nodes, so you don't want to do that. But there's only like a few thousand nodes in the merge point.
But then, wait, what? Then you have, okay.
Okay, first we'll do the first one.
So basically you just go, you traverse to the next one. And then the second one is say the next is.
No, so you give two
Hi, can I request help on this one? Okay, I'm not sure why this solution isn't working.
They tell you which one.
No, they don't tell you. You have to find.
You can take away the French
Oh,
statements.
Yeah, but they put the 50th one to find the.
It's not right, or is it?
No, it's not right. I think that's...
So, I have a question.
Yeah.
Is this list new? Do I have to reserve memory for this new list?
Yeah. You usually assume that you can modify the input, especially when you take a link list.
Sorry, what?
Because you have to make a new list anyway, because it has to be 7.
That's what I'm asking. Are we supposed to order this?
Yeah. So with linked lists, you almost are usually not allowed to modify the input.
Do you see her?
Because it's just so much memory. That's the goal is to create a new link list at this point.
Yeah, I haven't coded in a long time, but you see how they're all listed?
Yeah, you know why that's happening?
Because you didn't define it. You see, this is all
I mean, I think you can like redo some of those, like if you want
next, because we're the next one, right? But you didn't store it anywhere. So then,
Oh, now I get
that
it.
also
That's
is
okay. Now it's...
Or you can like 0,
That's pretty fun.
or you can like 0, 1. I mean like 0, 1 and then like that. Second list.
yeah.
There we go, thank you.
Yeah, I mean I got pretty sure to
Okay, well, if you well, okay, if there's a longer one, then you would find the difference in the longer.
Yeah, how much was
Because
it?
then it would be the same length. And then, not two, the amount, the difference, and the zeros.
No, it's 2. That's how you do that.
And then,
Okay, they're both singly within the same
and then, well, like, I think they would traverse
You don't know the difference.
and then each time you traverse, you add.
So how do you get like this one? And the right one.
If something is equal to 0, then add 1 to the index after that.
I don't think so. Because we keep it all on the
You usually find the
Instead,
like, I mean, the distance from the end, both of them. And then, whichever one is longer, you just and then you get the length. Yeah. Yeah, I mean, but it's not obvious. I didn't see them as ICPC, but as other friends.
I can be orange.
I got it.
it's equal or greater than 10 subtract 10.
Take a look.
That's true, I think
Alright.
Plus one, so.
Yeah.
Are you guys, you have something in mind? Some ideas? No? Yes? No? Yes? No? A little bit? Something? Alright. So Rehan will be going over the question in terms of your interviewing style.
Do people understand the question first of all? Does anyone have any questions? Okay. Yeah. So I guess I'll just like start off with an example. I mean, this example here is fine. So I guess we have. Well, I'm just gonna reverse the input. I mean, let's do this. Yeah, and then all we gotta do is sum them, right? So regularly, you just put 7 carry 8, right? And then so I guess just by doing this example, it kind of helps me think about what I need to do. Like I need to have this one carry variable, right? And like each step, what I'm doing is I'm taking 2 node values, summing them up, creating a new node, and then changing the carry, right? So it's basically like in one step, we want to create a new node, we want to see if we need a carry, and then make sure that the next pointers are correctly aligned, right? So I guess we can start with that base case, right? And then, like I like to think about like the general case, and then we can think about like the first case, which is like the first node. So the first node, what we want to do is instead of, the only difference is that we need to make sure that the carry is initialized to 0, and we want to make sure that the head, so we need to return the 7 pointer, right? So we can just start off with like a dummy pointer, and then we just make sure that dummy pointer, that pointer points to this one, and then we should be able to return this pointer, and then we get the answer. So I can start coding that. Do people have any questions about how this works? Or like the algorithm, anything I didn't describe correctly? Alright, now I'll just start coding it. Wait, do we have?
Yeah.
We have time. What's that?
Not creating that. Like just change on the case.
Oh, is that?
Whatever you can. Oh, whatever.
Look at the top here, because then you like check the size of it. Let's see. What's the function?
Let's see.
If you want to say what I've done so far, I just explain what I've done so far. It's just that I just create the initial dummy node, and I have a pointer to like the last node. You have a question?
Can you just turn the whiteboard a
Oh
little
yeah, sure.
Thank you.
Alright, can you see that?
Yeah.
Okay, yeah, so I made the initial dummy node, and I made the last node point to our dummy node. And then what I do is that the last pointer, I change its next pointer to a new node, and we initialize that node to be the sum of the two pointers that we're looking at, mod 10, so it's like 15 point source 5. And we just make it like it points to a null pointer for now. And then the carry is just the value divided by 10, right? So it would, and then, I guess I missed a step here actually, so that's just, yeah. So I made a mistake here. I forgot to add the carry. And then, yeah, and then this should work, but, oh,
The second one.
oh yeah, sure. Yeah, and then this should work for like the example, but there might be some problems if one of the linked lists is like longer than the other, right? Or maybe there's a carry at the end, so like you're adding like 90 plus 80, then you need that one instead at the end. So this is like a good start, but then we need like a little bit more after this. So I'll just go along with that. Does anyone have any questions about this stuff? Yeah. Oh, that's a mistake. Sorry. That's not me. My bad.
Good catch.
Yeah. Okay. Let's see.
Because pipeline, it'll automatically convert to rate, so you don't want it.
Alright, that should be it. All I did at the end was that I just checked if if either of those nodes are still pointing to a valid value, and then I just keep copying that value over, so making sure to set the carry to 0 here, and at the end if the carry is not 0, then we just create a new node with the value of 1. And what we do is we return dummy.next. So this dummy was what we used to initialize the last value, node the last pointer to. Yeah, any questions?
Alright, thank you for today. If this is too easy for you, just come back next time and we'll have harder things for you. If it's not easy for you, keep coming, because it's gonna get more interesting.